Alright, so now that we have the lazy sequences and we actually now have everything, we can take a look at the automated tester that judges your graded labs, each lab with the pass and fail possibilities. So there is 109 problems to choose from. Here in the repo there is the specification document, and then we had so these are all GPL, like I put all my examples, and then the automated tester 109 record file for all each problem, the first 300 test cases and the expected results, and then the data files, War and Peace, the famous novel that we get the English language text from, and then the words alpha, humongous list of English language words. So those are as data sources, and the automated tester, so when we run it, so let's do it here in the REPL project. So running the automated tester reads through your labs 109 file and finds all the functions that you've written, and then runs the test cases only for those particular functions. So 1 out of 1 functions of 116, so there's supposed to be 109, but I'm 7 more on the draft stage for the course. So then when we solve these lab problems, put them all in the labs109.py and run the tester again, and the tester even, so if you put your new function on top of the labs109.py, so these are executed in the order that you put them into the file. So these lab problems, there's so many, and none of them is a make work problem of any kind. So here, so as older I get, so the Onion Kelly cartoons, the more they start making sense to me. So here we have a typical millennial General Xer or some kind, and now that we're all on the lockdown conditions, so instead of what the youth go to your sock hops or whatever, listening to your hippity hop music, so maybe you can spend the time productively doing my 109 problems, so then everybody comes out better in the lockdown. Alright, so let's read through this automated tester, so what it's doing. So then this automated tester, so here we have a latest version, but then I'm gonna be occasionally updating this. I make new problems. So a couple of imports to pay attention first. So we calculate a checksum, kind of a digital signature of the answers that your functions return to my randomly generated test cases, and SHA-256. So for our purposes quite good enough, because it's not like we need the cryptography security here. Anybody who's good enough to do that kind of tomfoolery, so would be easier just to solve the first course lab problems. Time, so this one we have a function to get the current time, so then we can use it to measure the execution times. Speaking of which, I made these automated testers that my private model solutions typically take a second or two thereabouts to pass the automated test battery. So this one is on my Mac desktop from 2012. I've been meaning to update, but maybe next year. And then so perhaps your modern laptops are faster than that one, but none of the running time really should be in the minutes. So then that means that you have too many levels of nested loops in there. You're being a Slemiel, so to speak. Look that one up, and then maybe to do the logic with the fewer nested loops. So remember, every level of nesting in the loops adds an order of magnitude to the running time. Labs 109, so when you write the Python script, it's a module you can import like any other module. So execute the module in its own namespace, and then once it's done, so the namespace object is known as labs 109 in our script. So with that object I can access any function written in labs 109. ITER tools that we saw in the previous lecture gonna be handy in making all kinds of random test cases. Randomness, speaking of which, so here we have the random module again, but now to ensure that the pseudo-random, totally deterministic but chaotic sequences of random numbers are same for everybody, and therefore we set the fixed seed to be used, 1, 2, 3, 4, 5. Now this particular library, the random number generator, happens to have a guarantee that in all environments, so no matter whether you're running Python on a Mac or a Windows or a Linux or whichever, that you always get the same sequence of random numbers from the same seed. So this makes all these pseudo-random tests repeatable, and then they're the same for you and for me. And therefore, if we get a different checksum from the answers from the pseudo-random test cases, so then that means that at least one of the instances your function returns a different result than mine. Now it is perfectly possible that my function's wrong, this has been the case, but all of these problems have been independently solved by one other student, most by several, so unlikely that we get a checksum problems. And then the new thing that I added in this semester, because just the checksum failure seems so passively aggressive, there's something wrong, I'm not gonna tell you what it is. So now in the coding bad fashion, that you get the actual failing test case and you can reason about it. So we file in the record zip. Don't try to unzip this one in retrospect, I should have named this something else. So then the cutoff, so the first 300 expected results. So then when we're running the test, so we can detect the discrepancy and actually print out the discrepancy coding batch style. So typically, if there is some kind of bug in the function, so one of the first 300 test cases hopefully reveals it. And these test case generators tend to generate the test cases pretty much by nature in the increasing length order, so hopefully we get the shortest test case for us to reason about when it fails. Okay, so let's take a look at these functions here. I remember because 2 years ago, so when the deal was moving the intro courses from Java to Python, so I wrote just to refresh my Python skills, so rudimentary version of this, and then that became my own selling argument. So I went from 75% supporting the change, I went to 1000% supporting the change. So this kind of that we can just write one meta function, second order function, that takes an arbitrary function and test case generator. So a test one function, this is the heart and soul of this automated tester. So the function object to be tested, so that's gonna be the function that you write in your labs 109. And then here is a lazy sequence, so the generators from the previous lectures are gonna be put into good use here. And the expected checksum, or if not given, so then this is gonna output the checksum that it computed, so that I copy paste that to my the one that I release, and whether we are recording and whether there is known results. So when we're in the recorder mode, then we'll just try the first 300 test cases regardless and store the result. Okay, so function object, this is to be tested. So function objects in one of the secret names inside them, so every function object knows the name of its original definition. Then if it's a lambda function, anonymous function, so what this is, so let some Python expert explain. But then so we print out the name of the function. As you can see, the name of the function gets printed first. And then, so if we are recording, so notice how the print function, so if you don't tell it what file to type in, so then, well, the concept of file is a bit wider than our everyday language of meaning of a file. So file is just something that you can stuff into. But so if there is a file given, so if the recorder is given, so then we print the name of the function and 4 asterisk as the separator character into the file. So printing into a file, notice, is no different from printing from the screen. One and the same print function does both, you just give it a different target. And then if we have a dictionary of known results, so then we ask for the what is the known results for this function, or if there are no recorded results, so then there aren't. So this way I can add more functions to this framework without having the recorded results. And to test this one function, we're gonna need a checksum calculator, so create a new instance of the SH256 calculator, get the current starting time, so call the function time, you get a system clock time, millisecond precision, usually it's not the absolute value that we care about, but the difference between 2 points in time. So we take the start time, ask what it is, and then when we're done executing, ask for an end time. The difference between the two by definition is the elapsed time. And then we keep track, has the test function to be crashed, function to be tested, does it crash? I guess it's also function to be crashed if we can. So the tests are supposed to shake down everything and make every function squeal its weaknesses. So crashed, so far so not. So the first crash we cannot terminate. So in all these the problems, crashing is never the correct answer. The functions that we write are not supposed to crash. And then we have some kind of a test case sequence. Notice how we don't know and don't care. Is it the lazy sequence equals eager sequence? Was it made with a generator function? Doesn't matter. So we just loop through it and decorate it with the enumerate, so that the enumerate, remember, so the sequence, the elements, and then the running count number. So let's ask your function, given these arguments, this very strange looking thing. So normally we think of asterisk as a multiplication, a binary operator. Well, here it is used as a unary operator, so applied as a prefix operator like a unary minus. So this has nothing to do with multiplication, but this one is the tuple blow up. So expand the tuple elements into separate arguments. If you just say f test, so then the test is a tuple, it's one argument, there's stuff inside it, but the one argument only. So this one, suppose test is a tuple of 4 things. So then that blows this up into 4 separate arguments. So this way we can test the function regardless of its arity, as long as the test case generator generates the correct number of arguments for particular function. The same test one function handles the unary functions, binary functions, ternary functions. It's all good as this is concerned. We catch any exception, so crashes are not supposed to happen in the code to be tested. We mark that it's crashed and print out the crash report, and then once it's crashed, so then it's pointless to try anything more. Now, the thing with the sets and the dictionaries is that when we convert them to something that we can print and compare, so it's implementation dependent what order we're gonna get the elements. So we have a utility function that if something is a set or a dictionary, turns it into a sorted list before, so that we get the same thing that we can compare for equality. And then, so how do we take an arbitrary object and turn it into something that we can feed into something that is eating bytes? So let's convert it into the string representation, and then the string we encode into a byte stream. So this is the raw bytes that we get. So this is a standard encoding. So you and me, we're all gonna be getting the same bytes, and it is those bytes that we feed to the checksum calculator. So this way, you and me gonna get we're supposed to be getting the same answers, and therefore the same result strings, and therefore the same encoding into bytes, and therefore the same checksum. And if we are in the recording mode, so then into the recorder file, print the answer, but only the first 300 characters, because some of the functions they return the entire words alpha filtered. We can get a megabyte answer easily, so I don't want to have too many of those in the record. So first 300 characters usually is enough, and this is now enough recording, so then we'll break. And if the answer is known, and we are still within the recorded area, so some test case generator might generate a million test cases, we only save the first 300, so if we're within the first 300. So if there is a recorded thing, and then the result string is something else, at least the first 300 characters. So then we can now actually print out the actual test case, the test case position, and then the test case so this is the special function that makes not the human readable but the machine readable representation, and we ask the recorded dictionary what would have been the correct answer. Recorded, is a list that we get from the dictionary, so we can just access by the problem position, and then return the actual answer. So when these two differ, then same as in the coding, but you can reason what is going wrong. So do this for every test case. So a test case generator lazily produces all the test cases. And then, so if we're not recording, so let's ask for the current time, and therefore the difference between when we started and now. So that difference is the number of milliseconds that we worked, and the checksum, so we can get the hexadecimal digest representation of the current checksum. And then, so if the checksum's not expected, so then we print what it's gonna be. I just print the first 50 characters, should be quite enough. And then, so if not crashed and we got the correct checksum, at least the prefix is what was expected, so then we print this desired message success in let's run this again just to okay, so then it's just well, REPL is acting up, but there is success in the number of seconds. So this one only has such a few test cases that this cannot really be longer. So this is the logic of testing an arbitrary function with respect to arbitrary test cases. Scrolling down, so here we have a utility function. Notice that the Python source is raw text, so we can read through it like any text file, and then the file acts as a lazy sequence of lines, so enumerate through them, so decorate each line with the line number and the line, and then, so if the line so is a top level function definition, so starts with the def and a space, so then extract from the next character. Notice this is position 3, so extracting from the position 4 to the string method find, so this finds the position of the first occurrence of the open parenthesis, so that excluded, so anything in between is a name of a function, and the strip takes away the white space from beginning and end, so just in case the user puts some extra white spaces, so we don't care. It's good to make your code robust so that it doesn't, especially so dying because of unexpected white space, so that is just such an amateur hour that shouldn't be seeing that in this day and age. Then, so we in the dictionary say that this function so is now found in that particular line. So do this, so read through all the lines to build up a dictionary, so where did each function occur, and again, so sorting with the custom criteria, the test suite list that we'll soon be looking at, sort it, but so that you use x0 for the test case x, so is the name of the function to be tested. So we use the line number where that the function was defined, or so if the function wasn't defined, so then we use a different value that is so big that it doesn't matter. So sort the entire suite, and then so once the execution X is the context manager, the with block, so then even if something goes wrong, so everything gets cleaned up. So then we just return this suite that was sorted. So we get the list of test case generators and things as a parameter, but when a function receives a list or another complicated object, so then the function and caller, they share the same object, and therefore when we modify the contents of the object, they remain modified even once the function has returned, because the object suite is the same object in the object heap for both the function and the caller. So having all this, so just to test all functions, it is just a simple loop looping through the test cases, so asking has a function been implemented, if not just skip it, otherwise test it, and do this for all functions, and then the final report in the end, and that's it. So let's finish up. This video is getting a bit long, but let's look at one of these generators. So one of the problems, actually a bunch of them, so is chessboard generalized. So for example the rooks. So find how many squares on the chessboard generalized board n by n are so that there isn't any rook in the same row or the same column. We start by creating a fresh instance of the random number generator. Notice that there is a data type random in the random module. Give it a fixed seed, and then the entire future of this RNG is as destined as the train is followed to Destiny's track. So you and me, for the same seed, always get the same random numbers. Therefore, we get the same test cases constructed from those random numbers. So we're gonna do 1,000 test cases, and each one, so we calculate, if we make a random board size and how many pieces, so random number between 0 versus the size of the board -3, and the list of the pieces. So while the list of the pieces length is how less than what we wanna have, so generate the random coordinates, and if this isn't already in the pieces, append it as a tuple in the pieces. So this creates a list of board locations that are then gonna be chess rooks or knights or bishops or whatever. So yield the tuple of the arguments. Safe squares takes 2 parameters, so we give it 2 arguments. Scrolling down here, one more thing. So the Python singleton tuple notation. This is like the silliest looking thing, but it's because parentheses mean too many different things. So if you just say I parentheses, then there's suddenly precedence parentheses. So if you want the one element tuple, well, you know how, well, so you just have to put a redundant comma. So now this is a singleton tuple for a function that takes one argument. So that's how the Python is, but it's the economy in the number of different parentheses.